Hello, my name is Shuo Miura. I'm presenting our work on benchmarking actor-critic deep reinforcement learning algorithms for robotics control with action constraints. This is a joint work with collaborators from Omron Science Corporation and Kyoto University. In particular, Kazumi Kasara is the other lead author of this work. In this work, we considered action-constrained reinforcement learning. In action-constrained reinforcement learning, actions must satisfy constraints both during and after the training process before these actions are executed in the environment. This is an important problem setting to consider when we want to apply deep reinforcement learning to real robotic systems. This is because every input to real robots must satisfy physical constraints such as torque or power constraints of robots. Action constraints can also be used to ensure safety of robotics behaviors. For example, we can use action constraints to prevent robotics arms from hitting obstacles. The main contribution of this work is presenting extensive evaluations of existing and new algorithms for action constraint reinforcement learning. In this work, we focused on evaluating deep reinforcement learning algorithms based on the Actor-Critic architecture. In the Actor-Critic architecture, actor decides what actions to take, while critic learns how good these actions are. When the actor is updated, the critic is used to decide the direction for the update. We use two of the most widely used deep reinforcement learning algorithms for robotics control called TD3 and soft actor-critic. The most straightforward way to handle action constraints is projecting the output of the actor to the closest feasible actions. This has been used as a baseline in some of the previous works. However, there is a serious issue with this method. If we use the same formula for the actor update and take the gradient for the original actor, we end up ignoring the effect of the closest point projection, and the actor might not be updated in the correct direction. To solve this issue, previous works have proposed using differential optimization layers to perform the closest point projection. With this, we can compute the gradient for the closest point projection step, and the actor can be updated in the correct direction. Another previous work proposed decoupling the policy gradient and the projection step. This algorithm is based on the Frankel optimization method. We also considered a very simple baseline that treats the closest point projection as part of the environment. The only difference from the first algorithm is that the critic now is trained with actions before the projection. In other words, critic learn how good actions are given that actions would be projected to the feasible actions inside the environment. With this very simple change, we can avoid the issue of the actor being updated in the wrong direction. So far, we have considered methods that are based on closest point projection. However, there is no inherent reason to use closest point projection. One previous work called alpha projection proposed moving infeasible action towards some interior point in the feasible action space until these infeasible actions become feasible. Similarly, we considered another method that squashes the entire action space around some interior point in the feasible action space so that all the actions become feasible. Both alpha projection and radial squashing can be implemented as a final neural network layer of the actor so that the gradient for the actor can be computed correctly. For our evaluations, we used simulated robotics environments from OpenAI Gymnasium. For each environment, we considered different constraints inspired by power and torque constraints of robots. The results I'm going to show next are based on these constraints. Here are some results from our evaluations. The plot shows average errors after the training process. One main takeaway from our evaluation is that simple baseline method that trains the critic with pre-projected action is actually a very good baseline, performing almost as good as any other methods. This is in contrast to training critic with projected actions, which has been used as a baseline in some of the previous works. We also saw that alpha projection and radial squashing are viable alternatives to the closest point projections. We see that there is no inherent reason to map actions to the closest feasible actions. Lastly, we observed that the use of optimization layers and NFWPO comes with significant runtime overheads. The plot shows in log scale running times for different algorithms for different batch sizes. We see that as we increase batch sizes, the running times for differential optimization layers and NFWPO increase drastically. In conclusion, our paper presents a benchmark for evaluating action constraint reinforcement learning algorithms. All of the algorithms and problems in this work are available from our GitHub repository. Our evaluations led to some insights that are against the conventional wisdom in the field, such as the effectiveness of the simple baseline that trains the critic with pre-projected actions. Thank you.